Okay, so we are now at the final lesson of our solutions unit, section 10.3, acid base stoichiometry. And what exactly is this? Well, we've learned in the past couple sections what acids and bases are, and we learned in the reactions unit about the neutralization reaction where an acid and a base react together to produce salt and water. So we can use what we know about acids and bases to determine a concentration of a solution, and this is called a titration. So a titration is a procedure used to determine the concentration of a solution using a standardized solution. Well, what is that? That's a solution whose concentration is precisely known. And for this procedure, we need a burette. And this is a burette here in this picture. And both of them, actually. These are both burettes. And it's a piece of lab equipment which will help measure precisely 0.1 milliliter divisions. So we will use a burette, and in the burette we would put a titrant, and the titrant would go into the burette, and this would be our solution of known concentration. So this is where we would put our standardized solution. So experimentally, we will determine the volume from our burette. And this would be where our unknown concentration would be. Slide that up a little bit. In the Erlenmeyer flask. But it would be a known volume. So, just to recap, we would have our known concentration, our experimentally determined volume, our unknown concentration in the Erlenmeyer, and our known volume. Okay, so that would be our V, this would be our C, this again would be our C, and of course this would be our V. So we're going to learn the formula for determining how we would find this, the unknown concentration, and so on. So we have put our titrant into the burette, and then we need also an acid-base indicator. So the acid-base indicator would help us to determine if a neutralization reaction has taken place. It will determine the endpoint, and this is where the indicator changes color. So these indicators have to be chosen based on the solutions that you are using. And that's something that you'll learn more about later, and you can read about in your textbook. So the indicator would then go into your Erlenmeyer flask. Into your Erlenmeyer flask. So in a titration, we have what's called the equivalence point. And this is the point in a titration when neutralization is complete. We also call this the stoichiometric point. That's another name for it, the stoichiometric point. I'll write that down here. So this is the point where the number of moles of standard solution equals the number of moles of unknown solution. This is the point where all the hydrogen ions have reacted with all the hydroxide ions to neutralize the solution. So you could see here, based on this graph below, that the endpoint and equivalence point are not the same. Why is that? Well, this is because all the weak acid is neutralized and converted into its conjugate base. So for example, the hydroxide reacts with the hydrogen from the vinegar, and an acetate ion would be formed, and that would be your conjugate base. So then this conjugate base will react with water to produce a slightly basic solution. Okay, so it's not that important that you're able to explain that at this point, but I mean, it's helpful to understand why our equivalence point would be here at 7, and we are looking at about 8.2 if we're looking at phenolphthalein. Why phenolphthalein? It's would be around 8.2. The color change would happen. So an acid-base indicator is chosen to change color at the equivalence point of a reaction. And the color change is a visual cue that the equivalence point has been reached. The indicator changes color very permanently when you add a slight amount of titrant, and that's called the endpoint. So with phenolphthalein, you'll see it gets to be a really light pink. And that's the color that you would want it to get changed to. When it gets but you could add one more drop and it's going to turn extremely bright. And that means you're at the end point at that point. Okay? Okay. So a titration will only give accurate results when the endpoint coincides with its equivalence point. You want them to be close. Acid-based indicators do not change color with a specific pH value. However, rather we observe the color changes over a small range of pH. The acid-based indicator chosen for a titration must change color within the pH range when the equivalence point is reached. So on page 478 of your textbook, you can see the pH ranges of various acid-based indicators. So I'll just pull mine out and show you. Okay, so this gives you, it's better to see it in color. So let's just get this in the right spot. Actually, let's bring it over here. So you could see for if we have a strong acid and a strong base. So there's different situations that you will deal with. Here's phenolphthalein. The range, we could use bromothiamyl blue, methyl red. So they all have different ranges in which you would see the equivalence point. And this is showing you different indicators you can use and their different pH ranges. Okay, so you choose the proper one. We generally tend to use phenolphthalein. Well, in grade 11 we do. So it goes from 8 to 9.6. It goes from a colorless to a pink. And you've seen that color before when we have done some reactions in grade 10 and grade 11. Okay, so in order to know how to do titration, the steps are shown to you on page 479, and you can read through how you would do that. So hopefully we will get to one of those in grade 12. So, but we're going to learn how to do the calculations. We're going to focus on that because that's what we're going to be doing in this lesson. So let's take a look at that. So if we have 0.5 moles per liter solution of nitric acid, oh, there's an H missing in there, is used to titrate several 25.00 mil samples of sodium hydroxide. The endpoint was detected using bromothiamyl blue. And here's the data. So this is similar to what you would get in the lab. So you would have your initial reading would be at 0, and then your final reading would be for trial 1 would be at 8.00. And notice that your new initial, or your second initial would be equal to the final of the first one. Okay, and that follows through for the third as well. So it's asking, what is the average volume of nitric acid used? So we have to find each volume for each trial to find the average, right? So let's do that. So the first one would be volume 1 would be VF minus VI. So this would be our VI and this would be our VF. So that would be equal to 8 minus 0. So that's equal to 8 mils. And for our second trial, it's going to be the same. So it will be 16.12 minus 8 mils, and that would be equal to 8.12 mils. And for our third one, 24.62 minus 16.12 mils. Oh, sorry, that would be 8.5. So we would need the average, V1 plus V2 plus V3 divided by 3. So 8 plus 8.12 plus 8.50. Those are all mils. And that would be equal to, put that in your calculator, 8.21 mils. Okay? Okay, let's grab my calculator. So let's also write down what all the givens that we have. What we're being asked here. Calculate the amount concentration of the sodium hydroxide. So we have now found what's going in the burette. So we have found the volume of, the average volume of our which one are we finding? Our acid, the volume of our acid. So we're having, the acid is in the burette and the sodium hydroxide. How do we know? Okay, so we are told this is our concentration of acid. And we are told the volume of our samples of sodium hydroxide. So that's our clue. Our volume of our, because we know based on our note, like what we just wrote down, I'm just going to flip back to it so we remind ourselves, right, that we'll have a known volume of what's in our Erlenmeyer flask and an unknown concentration of this. So that's how we know that that's what it is. And we have a known concentration of what's in the burette. So that's how we know that that's the acid, okay? So that's how you know based on what's given in the question. So our concentration of acid is 0.500 moles per liter. Our volume of our acid is 8.21 mils. And we are required to, oh, well, what else are we given? We're given the volume of our base is 25 mils. And we're asked to find the concentration of sodium hydroxide. Okay? So how are we going to find the answer to this? Well, the equation that we use for doing titration questions is CAVA equals CBVB. Does it look familiar? It should, because we use this with our dilutions. So it's the same equation, just different situation. We're dealing with acids and bases now. Okay, so we have what's given, so let's go to the next step, which is we need a balanced chemical equation, right? We need a balanced chemical equation for our reaction because we have to know if it's a situation where we need to find the number of moles and make them equivalent. So we are reacting nitric acid, so HNO3. This may be given to you in a question and it may not be, so you have to be prepared to be able to write your reactions. So what's my nomenclature and reaction completion is still very important always. So sodium hydroxide. So we're double displacement, so NaNO3 and water. Okay. So we're going to convert all of our volumes into liters. Now, so we have our volume of our acid is 8.21 mils. So that's 0.00821 liters. And our volume of our base was 25 mils. Remember, zeros count in chemistry. That means we've measured to that degree of accuracy. So that would be 0.025 liters. Move some out of the way. And it says rearrange the concentration equation to solve for the amount N of HNO3. So C equals N over V. Well, so we're going to find our N of our acid is Ca times Va. And this is 0.500 moles per liter. Oh, I forgot to mention, we have to look to make sure that our equation is 1-to-1. It's balanced out. So I just automatically did it in my brain without thinking. So we have, in this case, two hydrogens, nitrate, sodium, and 1O. So it's balanced out. There's no need to do anything. So we have 0.500 moles times our volume of our acid. We will see an example where that's not the case, our next question, so keep that in mind, where it's not a 1-to-1 ratio. So we multiply that through. So we have 0.00411 moles. Okay. So we determine the amount of sodium hydroxide used using the mole ratio given in the balanced chemical equation. It's a 1-to-1 ratio, right? So that means that the amount of acid equals the amount of base. But we'll just show that mathematically because, like I said, in our next example, that will not be the case. So 1 mole of sodium, what does that mean? 1 mole of sodium hydroxide to 1 mole of our acid, HNO3, nitric acid, equals X moles and 0.0411. Right, we already have the answer. It's going to be X is equal to 0.0411 moles of NaOH. So now we use this amount and put it back into our equation to find out the concentration of our base.